We're going to start today by changing gears. So we finished going over statics yesterday, Monday, and so we're still talking about rotational motion, but now we're going to talk about angular momentum. By the way, if you didn't see it, go over the lecture notes from Monday because I did include a worked out example that uses the steps for which you can apply the steps that we went over at the end of lecture on Monday. Right, so we're going to talk about angular momentum. So the first thing to do is to we know that there is this correspondence. Let me back up just one moment. So it looks like we're making good time on material to cover. So I'm going to try to go a little bit slower. I'll be happy to take questions today. So just keep that in mind. Right, so we know that there's a correspondence between angular motion and translational motion, right? Like you have F equals ma, you have tau, torque, equals I alpha. You have translational kinetic energy is 1/2 mv squared. You have rotational kinetic energy is 1/2 I omega squared, and so on. There is this correspondence. So the first thing that we can do is we can look at how the angular, or we can try to use this correspondence to come up with a parallel for the translational case to try to come up with some angular version of momentum. So this would be, as is described, this would be angular momentum, right? Typically, we just shove the word angular or rotational in front of the word, and that makes it angular. So we're going to use the traditional like correspondence. So for the translational case, translational momentum, we have the vector p, which is momentum vector, equals mv. So for the angular case, using the correspondence, we would have the letter L, which is the letter we use for angular momentum. Don't ask me why L is used. I have no idea. Well, what's the thing that corresponds to mass? Well, for angular motion, the thing that corresponds to mass is moment of inertia. And the thing that corresponds to velocity is angular velocity. So we would expect something like this. L equals I omega. And so the units of this thing, the units of L, would be, well, I has units of mass times meter squared. Omega has units of inverse seconds. So this would be kilogram meters squared per second, or joule seconds. Now, again, just like how we did not want to use joules for torque, we really don't want to use is it for torque? Anyway, we don't actually want to use this joule second business for angular momentum, but occasionally it pops up. So I'm just telling you this to keep it straight and narrow. So just like force and torque, remember force is newtons, torque is Newton meters. P and L, momentum and angular momentum, differ by a factor of length. Remember, the units of momentum, it's mass times velocity, so it's kilograms times meters per second. So angular momentum is kilograms times meters squared per second. So they differ by a factor of length. Torque is newtons times meters. Angular momentum is momentum times meters. And this isn't a coincidence, right? That this is like all of these things have parallels for the correct reasons. So if such a thing exists, and I'm telling you it does indeed exist, if such a quantity if we can write a quantity called angular momentum, L equals I omega, then we would expect that there is a rotational version of the impulse momentum theorem. Remember, the impulse momentum theorem was basically a statement about when momentum is conserved. So if there are any external impulses, remember impulse is force times a duration. So the impulse that you apply is how much force you apply times how long you apply for. If there are any external impulses, then translational momentum is not conserved, and it tells you how much translational momentum changes by. Similarly, we expect something similar for rotational motion, something like you apply a torque for a duration, and that tells you how much the angular momentum changes by. So again, by the correspondence, the translational impulse momentum theorem is F, and instead of using deltas, I'm going to use D's, but just keep in mind that a dt is just a really small delta t. This is dp. The angular one, we know how to do this. We just substitute in the things that should be substituted in. So F becomes tau, so that's the rotational version of force. So dt is just dt, it's just a duration. And then the rotational version of momentum would be angular momentum, dl. And this checks out because we know, so just like how regular momentum is related to velocity, angular momentum is related to angular velocity. And so this kind of equation makes sense. We know that if you apply a torque to an object, i.e. if I take my phone and I apply a torque, we know it causes a change in the angular velocity, i.e. if I just applied a torque and this was freely rotating, it would start rotating like this. So its angular velocity would change. And so in fact, it makes sense. Applying a torque for a duration should change the angular momentum because the angular momentum includes the angular velocity. And also, we would expect that the mass of the object, or how the mass is distributed, i.e. the moment of inertia, should play a role in how much its speed changes by. So that's why angular momentum should be related to an applied torque, or change in angular momentum. So we can rewrite this just like we did for the translational impulse momentum theorem to get the rotational, let me use V, to get the rotational second law, or at least the momentum version of the rotational second law. So remember when we had, when we were talking about translational momentum conservation, we had the impulse momentum theorem. We could divide both sides by dt, and we would get that F equals dp dt, which is a statement of Newton's second law, especially once you substitute in that P is mv. Because if the mass is constant, you can pull the m out of the derivative, and then you get the force is equal to the mass times the time derivative of velocity, which is acceleration. So we can do the same thing here, and we end up with, so we start with torque, or tau dt equals dl. And so that leads us to that torque is equal to dl dt. And that's just another form of the rotational second law of the rotational second law of motion. If you, for example, you could write L equals I omega, and so long as I doesn't change, then that would mean that dl dt is I d omega dt, which is just I alpha. Now, this is this is only if I is constant. Now, these formulas, the ones that depend on time derivatives of momentum, these are more general than the standard issue F equals ma, or tau equals I alpha. And there's a reason for that. So the angular momentum can change in more ways than one, right? You could change the angular momentum by changing the angular velocity, but you could also change the angular momentum by changing the moment of inertia, right? Moment of inertia is not just mass, it's also how that mass is arranged. So if you were to rearrange the mass, you might change the moment of inertia. And so this formula is kind of the preferred one because it incorporates both how the angular velocity and the moment of inertia change. And the same goes for F equals dp dt. However, typically, in most systems that we consider, mass is conserved. Like that's not always the case. Like if you're like pouring sand from a bucket into like a moving, I don't know, like a moving wagon or something, the mass of the wagon is changing, right? So in that case, you might want to use that F equals dp dt. But for most of our cases that we're concerned with, it's just enough to just use F equals ma. because we're talking about constant mass systems. However, the reason why I'm harping on this so much is because there are a lot more situations where you can change the moment of inertia of a system without like adding extra stuff to your system. That's a lot easier to do. And I'm actually going to demonstrate an example of this later in a lecture. So keep in mind that these two things are very nearly equivalent, but this version, tau equals I alpha, is kind of more restricted. It's like it's true in fewer cases. So I just want you to keep that in the back of your mind. Right, so well, there's one more thing to talk about that uses the correspondence. I want you guys to recall that force and torque are related by a cross product. i.e. torque equals r cross f, right? Where r is the moment vector and f is the force that's applied at the end of the moment vector. So what can we do with that? Well, let's, we have dl dt. That should be equal to torque. That's what we just showed. But torque is equal to r cross f. So this could be written as r cross dp dt. And this equality that I'm about to do, assume r is fixed. Is there also, no, there is not vector division. It's not a thing. If the moment vector r is a fixed quantity, or more precisely, if the cross product of r with the vector p, if the projection of r, if the perpendicular projection of r is fixed. But anyway, if we assume that r is fixed, then you can put r inside of the derivative. And so this would become d dt of r cross p. And so what we find, at least for a single object, this is true, because for a single object, the r value won't change. Like it's, how do I want to phrase this? I'll just leave it at that. So for simple systems, we can then write that this is relating these two things back to each other, that L is just r cross p. And so this is just to say that just like how torque is r cross f, L is r cross p. So you take the momentum vector and you cross it with this new vector r. Now the question is, what is the vector r referring to? So the r, when we talked about torque, that was the r that was the distance from the axis of rotation. That was the displacement vector from the axis of rotation to where the force is applied. So that r got carried through all the way. And so that r still is the distance from the axis of rotation to the place where, or yeah, it's hard. It's the same r vector. First, to plug into the equation. So we find L first.
Wait, so you said r was the distance from the axis of rotation to the place where what happens?
R is so this r refers to the axis of rotation. It's the displacement vector from the axis of rotation to the location where the force is applied. By the way, this whole calculation, this is just for a point mass. All of this applies for a point mass only. So if you were applying a force to a point mass, that vector r is the vector from the axis of rotation. Like say the point mass is tied to a string. It'd be from one end of the string to the other end of the string. And then that force is applied on the point mass. And so what the r here refers to is it's the same r. It's the r from the axis of rotation to the point mass, and which is also coincidentally at the exact same location as the object itself. And so this r, traditionally, the way we would understand this is we would write this r as the vector that points from the axis of rotation to the object that's moving with momentum p. So let me draw a picture. So first, we need a reference point. Just like for torque, we need a reference point for this angular momentum. So the standard thing to do is we put the origin of the system, i.e. where x and y are both equal to 0, for example, at that reference point. And that reference point is traditionally the axis of rotation, but it doesn't have to be. Then, in that case, the vector r points from the origin to the thing with that momentum, to the thing with momentum p. So here's a picture. So here, say we have our reference point here. That might be the axis of rotation. It might just be some arbitrarily chosen reference point, either way. And let's say that we have an object, say over here, that's moving with some velocity v, and it has some mass m, so it has some translational momentum, m times v. Then the vector r that we cross with it to find the angular momentum is this vector r. So in this case, I'm going to put an m up here, and this vector I'll label down here. So in this case, the angular momentum vector to the what with momentum p? To the thing. Sorry, I left the word. So the point is because we're dealing with a point mass to the thing. God, I'm terrible. To the thing with. There we go. To the with. So unlike for torque, which we calculate as r cross f, which works for extended objects, this formula here that I've given you only works for point masses, basically, or for things that we can treat as point masses. And so the vector r points to the point mass. And the reason why that r vector, which was the location of where the force was applied, is also the location of the object, is because there's only one place to apply a force on a point mass, and that's on the object. You can't apply it anywhere else. So that's great for point masses. What if the rotating object is composed of lots of particles? So generally, by the way, this business of angular momentum concerns itself with like how much, just like how momentum tells you how hard it is to get something to stop when it's moving translationally. Angular momentum is kind of how hard it is to get something to stop rotating. So when we're talking about all of these things, we're talking about things rotating, like things or a thing rotating about some axis or orbiting an axis or something like that. So if the rotating object is composed of lots of particles, like think like any normal thing has a whole bunch of atoms in it, rather than just one particle, then all we do is we just add together the angular momentum of each particle. AM is my abbreviation for angular momentum, by the way. So the way that we would do this is, at least as far as magnitudes go, the angular momentum of a system would just be the sum of over I, where I is however many particles you have. So something moving in a straight line still would have angular momentum around a reference point. Yes, Jason, that's precisely it. And actually, we're going to get into that in a bit. But yes, that is true. Right, so this would be the magnitude of the sum of Ri cross Pi. So we would find the angular momentum of each piece and then add them all up and then find the magnitude. And so we could rewrite this as just the sum of MIVI perp times Ri. I need to be careful here. There might be a mistake in my notes. Okay, so this is actually fine. just to explain my potential confusion, is that there was a potential issue with the sum of the magnitudes not being equal to the magnitude of the sum, right? So if I had put the magnitude symbol inside the sum, the answer could potentially be different. But because all of these objects are a single extended thing, it's just like a whole bunch of things that are glued together, all rotating together. Because of that, all of their angular momenta point in the same direction. So in that case, the sum of the magnitudes is the same as the magnitude of the sums. It's a specific case, but it works for a single extended object where you don't have different pieces rotating at different rates. Now, as a reminder, the velocity so by the way, this is the magnitude, or it's the perpendicular magnitude of the momentum. So it's mi times vi, and then we take the perpendicular part of v because it's a cross product. That vi, that is perpendicular to the position vector. So let me be more explicit here. The velocity perpendicular to the position vector and the position vector comes from the axis of rotation, is just the radius, and I'll draw a picture here in a minute. It's the radius times the angular velocity, which is v perp equals r omega. And so just the picture here is, if you have some extended thing, here's your axis of rotation. If we're just looking at it like a single chunk here, if this whole thing is rotating, right, the perpendicular aspect of its velocity relative to this this axis, that is just its tangential speed, right? So that's why v perp is just r omega, where r is the distance here. That's all we're saying, because that motion is perpendicular to the vector that points from the origin to the location of the object. So from that fact, we can write the following result, that the angular momentum L is the sum of mi, this is the magnitude, by the way, so mi being the mass of an individual chunk, times ri omega, each chunk rotates with the same velocity, same angular velocity, right, because it's all glued together, times ri. And so this is equal to a sum of mi times ri squared, and then we can factor out an omega. But remember that the sum of m times r squared for all of the different chunks, that's how we define moment of inertia. So this is just I omega. So all of this that we just did was just a way of showing that, in fact, this thing that we hypothesized was that this was correct. That was something that we required. So as long as the angular version of the impulse momentum theorem is correct, we use that to get the angular second law, and then we used that angular second law and this the fact that torque is r cross f to get L equals r cross p, and so on. The fact that there is an angular impulse momentum theorem indicates to us that we were correct, that indeed it is true that angular momentum is just I times omega. That was a correct move to make. So this is a good thing. It's a check mark. Right. So there are other ways to compute angular momentum besides just doing r cross p or I omega, right? So let me just outline one. So anytime you have a cross product, there are multiple ways to compute it. So we can use the same moment arm trick. Remember when we were doing statics on Monday, the same moment arm trick as for torque. So we extend one of the vectors, we find the perpendicular distance, and so on. So the angular momentum of a point mass is equal to mvr perp. That's also true. It's also mv perp times r. Those are equal things because they're both just mvr times the sine of the angle between them. The sine of the angle between them, that's kind of carried around by this perpendicular bit, right? Just consider, like, you have two vectors. The sine of the angle between them gives you this distance effectively. So we can use that trick like we did for torque. So let me draw a picture here. Let's say that we have a pivot point here, or an axis of rotation. And let's say that we have an object, a point mass, moving with some speed v. Trying to draw it well. Moving with some speed v this way. So the way that we can find our perpendicular is just extend the velocity vector in both directions. And then this length here, that has length r perp when this is a right angle. So it's the exact same thing. We just instead of extending the force vector, we extend the velocity vector, and then we find the perpendicular distance. Now, just as an aside, just a thing to think about, if you have a moving object, like imagine that instead of this thing being a single point, imagine it was like a phone, right? If that thing's just moving translationally, if it's an extended object, that's what a phone is, but it isn't rotating, like if it's not doing this as it moves, right? If it's just kind of coasting, then let me actually write this. If a moving extended object isn't rotating, we can treat it as a point mass at its center of mass. For the purposes of computing L. So this is just to say that if an object isn't like rotating about its own central axis or something like that, then the only component of its angular momentum that actually contributes is the angular momentum that you would get if all of its mass were concentrated down to a single point. Now, the consequence of this is that the way that you find the total angular momentum of a system is you find the angular momentum treating all of the mass as if it weren't rotating. Like, imagine that you have this thing just moving while it's rotating. First, you would find the angular momentum about some reference point as if it were just not rotating at all. And then you treat all of its mass as if it were at the center of mass, and you do this calculation here. And then later, you would find the angular momentum of just this thing rotating about its own center of mass. That would have some other associated angular momentum with it. And then you would add those, and then you would add those two numbers is what it boils down to. And we'll be more explicit about that later, but that's kind of a consequence of this idea. And it's closely related to the parallel axis theorem, by the way. Great, so I've given you a few ways to find angular momentum. For the most part, the easiest way will just be to either do r cross p, like if it's just for a point mass, or if it's for some extended thing that's just rotating, then you would just do I times omega. And so once you know how to compute angular momentum, then you can ask, okay, well, what is it useful for, right? And so just like how momentum was only useful because there were cases where it was conserved, angular momentum is the same way. So let's talk about angular momentum conservation. So just as a quick reminder, angular momentum is, torque is the time derivative of angular momentum. Useful fact. So that means that if the net torque on the system is 0, that implies that dl dt is 0, right? And that just means that L as a vector doesn't change. And all that means when a vector doesn't change is that it's conserved. So if there are no external torques, or if the net external torque is 0, that means that the angular momentum of the system is conserved, just like how if the net external force is 0, translational momentum is conserved. So let me give a quick example, just a thought experiment for you guys to do. So suppose a spinning plate, and I'll draw a picture in a minute, is dropped onto a stationary plate, or like maybe it's like lowered onto a stationary plate, just so there's no crashing and breaking. And the stationary plate is at rest on a frictionless surface. What happens next, right? Like after they come in contact, what happens? Well, we should at least be able to get some intuition for this. So the picture here is you have a plate that's rotating, and then it's dropped onto a plate that's stationary, which is at rest sitting on a table or something. So this is kind of like that situation where we had a book on a frictionless surface, and then we kind of shot a book at the top of it, so then they would like slide together. And so much like what happened there, where the top book, the one that was shot at the bottom book, slows down, and the bottom book speeds up until they're both at rest relative to each other, but they're moving along the surface. A similar thing would happen here. The friction between the two plates would cause the top plate to slow down while it speeds up the bottom plate until they're both spinning together at the same rate. So hopefully this checks out with your intuition. One moment, till they're rotating at the same speed. So that's a good thing. And we could apply angular momentum conservation here because the only forces present, the only torques present, would be torques produced by the friction between the plates, rotating at the same speed. So the thing to remember here is the sliding book example. All right, so this would be one example of angular momentum conservation, a situation like this. Now I'm going to do a demo here. I'm going to see if I can get the, let's stop the share. I'm going to see if I can get the camera set up properly. This is the only demo that I actually can do at home because I have a chair that can spin. Needs to be way further back. I usually have it like on top of my printer or something. Okay. Oh boy, what happened? Oh, okay. All right. Let's see if. Oh, that's the wall. See if I can get it to stay in place by using maybe a soda can. It's always hard to set up. All right, let's go. Let's see if you can see me in a chair. All right, so, okay. Let me angle it down just a smidge. You can see the chair now. Pardon my living room being a mess. We had to move stuff out of the garage a few days ago, or a few weeks ago. We haven't cleaned up yet. Right, so these are just two 5-pound like dumbbell weights. Or I guess barbell weights. So what I'm gonna do, let me move this basket of fruit out of the way, and this basket of nothing out of the way. So what I'm going to do is I'm going to sit in this chair I'm going to hold these out. Now, this will test my strength because I'm a pretty skinny guy, and that's hard for anybody. But what I'm going to do is I'm going to hold these out, spin myself up, and then you'll see what happens next. So, oh, need to make sure you don't hit the wall. So just observe what happens as I bring the weights in. I speed up pretty significantly as opposed to being out. Slow, faster. Slow. That's a good way to get dizzy. Let me try this one more time just so you can see it again. Spinning, bring it, oh geez. And then out, slow down, then in, speed up, and so on. Right, so, okay, now you get to watch your instructor be very, very dizzy and try not to fall over. Actually, I've not a great look for me. I've heard that if you look at someone's eyes while they're dizzy, I'm not dizzy anymore, but my understanding is that your eyes will like flick back and forth or something. I don't know, I've never seen it before. Anyway, hopefully that was somewhat interesting. And the point was to illustrate that something weird was happening there, right? Like even there was nothing external to the system. So how could it be that I was changing my speed like that? That was the point anyway. Let me just get this set back up to continue the lecture. Come on. Come on. Back in place, get in my chair. I'm significantly less dizzy now, which is good. Right. So, yeah, no, if Arnold figure skated, then, and he was, holding out like 80-pound weights, he would, probably die. That amount of the speed that he would, or the rate at which he would change his angular velocity would be very, very large. Anyway. Let me go back to sharing my screen. My mic is weird. Oh, you guys probably couldn't hear me because the mic is the mic is the webcam. Okay, at least you could hear me. That's good. All right, let's continue. Okay, well, I'm glad that it was loud and clear. All right, so now we need to figure out or try to think about this for a minute. So I'm just gonna put in place this me spinning demo, just so then you guys know what I'm talking about if you look back at the notes later. Right. So the strange thing about what you guys just saw, and this was really strange to me when I first saw it too as an undergrad. The strange thing is that there's no system where you just have translational motion, where a thing just suddenly gets faster and then suddenly gets slower without any external forces acting, right? So the system that I was in, me and the chair, those were the only things. Yeah, that'd be funny. Those were the only things that were actually in the system, right? I know. By the way, we're going to go for 10 minutes longer, like we usually do on Wednesdays. Those were the only things in the system, and yet somehow I was changing my speed. You can't do this with a car. If you put your feet on the gas in a car, there's a road that's applying additional force to you. That's like that's an external force. So how is it that I can change my speed with no external forces? I can change my angular speed. That's the strange thing here. It's like, it's kind of intuitively weird. Yeah, I mean, physics is witchcraft. Like, I'm 100% convinced. So What makes what I just did different from a translational system where you just have like translational motion is that the angular momentum of a system can change without any external forces or without any external influences. Sorry, not the angular momentum. The angular momentum is fixed. The moment of inertia. And I'm going to run out of space. Moment of inertia of a system can change without any external influences. So the corresponding thing that you would see here would be like, imagine you have a wagon just going along with its, like there's no external forces or nothing fishy going on. Or how about, perhaps better would be like a spacecraft just flying through space, and then somebody just like hucks a whole bunch of sticky glue to it. So that would increase its mass, and so it would slow down. That's similar to what happened here. And the reason why we can do that here without having to add anything extra is that we don't need to, it's not the case that the only way to change the moment of inertia is by changing the mass. We can also, without changing anything external, without any external influences, we can also change the position of that mass. We can change the mass distribution, which affects the moment of inertia of the system. And so that's what you saw me doing. So I'm going to kind of step away from that particular example. We'll talk about some more general things to try to understand what's happening. So let's consider a rotating system. System rotating about a fixed point. So I'm going to draw my standard issue blob. Standard issue blob. And let's say that there's just some fixed point there. It's an axis of rotation or something, and the whole thing is rotating about it, right? So in this case, every particle in the body, every particle, every chunk of mass, whatever you want to call it, is following a circular path, right? Like they're all going in a circle around that point. And so what that implies, we know what happens when a thing undergoes circular motion, right? That means that every particle experiences an acceleration, except perhaps the one particle that's at the center experiences acceleration, right? And in particular, it experiences centripetal acceleration, right? And what that implies is that every particle must have a force on it. Because if F equals ma, that's still true for a given chunk of mass. If it experiences some sort of acceleration, it has to experience some sort of force. Now, generally, for extended bodies like phone or whatever, that force is like the attractive force between molecules and so on. It's like the force that holds the thing together. So the question then is, if every particle experiences a force, how can it be? And this is the case for any rotating body. Every particle in that body experiences a force on it. How can it be that the net torque on any rotating body is ever zero? Like, how is that just possible if there are a whole bunch of forces? That would have to be some, in the words of Juan Carlos, there would have to be some witchcraft to have everything cancel out perfectly. But it's not that complicated, actually. As a reminder, circular motion implies that the acceleration vector points towards the axis of rotation. Right? That's what it means. That's what centripetal acceleration means. It means centripetal means center seeking. It points towards the center. And so if we just look at let's take this. chunky boy, put it right there. Let's just examine just a single particle that's going around in a circle, maybe one here. So this particle would go around in a circle like this, right? But the acceleration vector for this chunk of mass would point to the center, where here is the pivot. Sorry that the words are small. And so the acceleration vector points in the same direction as the force vector, F equals ma. So this implies, so that double arrow thing means, that the force vector is parallel to the vector that points from the pivot to that chunk of mass, r. And what that means is that the torque, which is equal to r cross F, is 0. So the whole point that that I'm making is that even though every particle has a force on it, the torque on every particle from that force has to be 0, because that force points in the direction towards that pivot point. So we can talk about this idea that a force pointing in towards a particular point gives no torque generally. So I'm going to define this idea for you. A central force, this is a definition for a technical term. God, I can't draw a straight line for my life. Central force is a force, and that force can potentially act on many objects, which acts, or which can act. To get this definition right, can act on many objects. That is directed directly, I know it's a terrible double use of that word, directed directly toward or directly away from a single point in space. So what this is all to say is that in general, central forces do not exert torques about their central point. And the reason for that is precisely the reason that I gave above, which is to say that if the force points towards some pivot point, then that force will produce no torque. And what that implies, because they produce no torque, the angular momentum, wait a minute, am I missing a page? No. Angular momentum around the central point is conserved. So the angular momentum, by the way, cares about what point you're calculating it about, just like how moment of inertia cares and just like how torque cares what your pivot point is. The angular momentum also cares about where your pivot point is. So if you choose your pivot point to be the location where all of the central forces are like attracted to or repelled from, then using that pivot point, angular momentum is conserved. And that's just because they're all, like that central force doesn't produce torque, and so there are no external torques, and hence no external angular impulses. And so, this going back to how this rotation occurred, or how like this the spinning me demo, we can finally explain that. When the weights are pulled closer together, closer to the center rather. By the way, notice when I did this, I pulled them to me. I pulled them to me, not like, but one of them off to the side, right? I pulled them to the center, to the axis that I was rotating around. When the weights are pulled closer to the center, the added force that I apply is a central force, i.e. it's pulled towards the center of rotation, towards the axis of rotation. And so this provides no torque. which leaves angular momentum unchanged. But the trick here is that the angular momentum was conserved because the force that I did conserved, or did no torque because it was central force. However, what did change, so the angular momentum didn't change because of that reason, but what did change was my moment of inertia. So the moment of inertia of the system decreased because I brought mass closer to the axis of rotation. And the implication there is that because the angular momentum is conserved, it doesn't change, and angular momentum is moment of inertia times angular velocity. If the moment of inertia goes down, which is what I did, the angular velocity has to go up. And that's why I sped up when I pulled in the weights closer to my body. All right, so I'm going to end it here. We're going to continue talking about this thing next time.